Hello, good afternoon, everybody. Welcome. We are just admitting the people that are. Well, good afternoon, everybody. Okay, so we have still people entering in the webinar, but we'll admit all of them as soon as we have here new people entering. Okay, so welcome. This is the first webinar of a consortium called Computer Science for All. Okay, I will start sharing my screen. I will start sharing my screen in order for all of you to see the slides that we have prepared for this session. So let me just... Okay. So good afternoon. Welcome, everybody. I will start by introducing our team, okay, the presenters team. So my name is Luis. I'm the co-founder and president of INSICO. Okay, INSICO is the one of the members of this consortium, this Computer Science for All consortium. And together with me, I have Professor José Nuno Oliveira from the University of Minho and also founder of INSICO. And I have Inês Guimarães, also a member and general manager of INSICO. The three of us will lead this webinar, and it will finish it. So it will be a 3-hour webinar, and will finish at 7 o'clock. And I'll just introduce the main purpose of this consortium. Okay, that includes three entities. So INSICO, Collectic, so a non-profit association from Barcelona, and Open University in UK. Okay, this consortium aims to promote adult education, and so that's why all of you have been invited to this webinar, and we'll share with you some of our of the things that we are doing and have been doing in these last few years, bringing into the educational system innovative pedagogical practices, and our main goal is to boost learning and application of technology and tools. As you will see, we are doing this focus on computing and how to learn computing in order to allow the young generations in particular to live in this new world in which we all live. Okay, so also one of the main goals of this consortium is to promote the use of techniques for non-formal education, okay, both for adults and kids, and also because we really think that, of course, it's important to train all these young generations, but in particular, and very important, and this is in fact the main goal of this Erasmus project, is to think and try to put into practice how should we learn, adults, professors, and all the people that are interested on these areas, how should we train them in order to be able to train youngers, so kids and teenagers, to be adapted to this new way of thinking and new way of working, and to be able to solve the problems. But of course, nowadays, every time we are talking about solving problems, we are talking about using computers, and in order for us, all of us, to use computers in the right way, it is, in our view, absolutely crucial to know about computing and how computers work and how everything is possible when we are leading and working with computers. Okay, so we will divide this webinar into 3 parts. Okay, the first one will try to explain to you how we see all this in terms of fundamental skills and fundamental knowledge that will allow us to talk about computing. And this is what we call the new trivium, okay? That includes the how we learn and how we use the mother language, how you use and explore mathematics, and how you will then explore computing, okay? As you will see, all these 3 things are connected, strongly connected by the language and by the linguistic purpose of all these matters. Then on the second part, we'll try to explain in detail how we see and what is in fact, based on our views, of course, and our convictions, what is in fact computational thinking. Okay, there are lots of noise around this. Okay, it's a popular expression, but we'll try to explain to all of you what are our thoughts and what we really think about what is computational thinking. Then we'll have a short break of 15 minutes, okay, in order for all of us to rest a little bit. And then on the third part, we'll have an hands-on activities. Of course, that all of us are connected remotely, okay, and we are doing this webinar. Typically, we do all these hands-on activities using pen and paper or using computers. But of course, what we'll do here is to show and also to launch some polls for you to answer, and at the same time to show you how we deal and how we do hands-on computing activities when we are dealing with people that we are training. Okay, so the first 2 parts will be led by Professor Zanuno. Okay, at the end of each part we will stop and give you time to put your answers, okay? And feel free to put the answers that you think are relevant for all the things and topics that we will discuss here. Also, at the end of the second part, we will do the same, okay? So we will give you time to put questions, and we'll of course ask all of you that wants to put some question to raise your hand, okay, by using the team's infrastructure, and so to raise your hand in order for all of us to guide the questions that all of you can put on this webinar. And after the break, we'll have these hands-on activities, as I said, and at the end and as well, we'll stop again and we'll open for discussion and also open a few minutes to allow you to put your final questions to everything that you have heard during this webinar. Okay? So at this moment, I think that we have more than 100 people registered and attending this webinar. And so I will now stop sharing my slides and I will put control on the hands of Professor Zenon Oliveira. And I hope that you enjoy what we will share with you today. And please feel free to put questions at the end of each part, because it will be important for us also to receive your feedback and to think what you think about what we are saying here. Okay. So Professor Nun, I'll stop sharing my screen now.
Okay.
And control is yours.
Okay. So can you please confirm that you are seeing the slides? Okay.
Yes.
Good. So let me start by thanking all the audience for their interest in this webinar, in which we are going to explain or describe the approach that at NSICO we are following in this topic. And the topic is the topic that brings us together today. It is consensual that computing should be introduced in schools from a very early age. The problem or the question, the matter is that approaches to teaching computing vary a lot. And so our approach privileges concepts over technology. So it starts in what we call unplugged mode. And I will try to explain to you what this means, okay? But I will start from quite early in the discussion, because if we look at the archaeology of education since classical antiquity, we know that there were seven subjects. The base ones were the trivium, where people would study grammar, logic, and rhetoric. And then the quadrivium with arithmetic, geometry, music, and astronomy. And it's from the trivium that we take our movement at this stage, because there is some relationship between these three words and what we are doing. So grammar is the study of the architecture of language. Logic enables one to reason. And rhetoric has to do with communication. Rhetoric was a discipline where using some language, so following the grammar of that language, people would understand, would learn how to communicate using that language. Eventually, grammar and fused with language, and then gave. I think every country has in basic education the study of the mother language. Logic and maybe with something from the arithmetics of the quadrivium led to mathematics, and somehow rhetoric was lost. Of course, it depends on different fields, but for instance, in people studying mathematics engineering, it disappeared. And actually, there was what is sometimes called the big divide. At some stage, people decide, I'm going to do arts or I'm going to do science, with a complete division of these two topics. What happens is that this big divide has led to a nefarious disjunction in the area of specialization. This may have happened in the end of the 19th century, when people sort of said, wow, it's becoming expensive to teach Latin to engineers, mechanical engineers, because we want their time to study other topics in their specialization field. And so the old man, I mean, the old view of the Hellenism and Renaissance was lost. In those old times, people would paint, they would write poetry, they would prove mathematical theorems, and they could actually invent mechanical objects and artifacts. So that was lost, okay? But it has have some really disastrous consequences. I teach at the university, and year after year, I realize that the students have less and less command of language. They don't want to, they feel nervous when they have to speak. They don't understand written text. And sometimes if you ask them something, if you put some text a little bit longer than a mobile phone message, they feel lost. So they are losing control of language. And actually, there is nothing, I will quote a famous writer and thinker on this on those fields. There is nothing more powerful than someone who is articulate and who can think and speak. It's power, and I believe this is true. Meanwhile, amazing advances in digital technologies enable digital communication. So what happens now is that perhaps we need rhetoric uh, twice, because now we have two kinds of communication: human and human machine. And when one thinks about human machine communication and think about programming a machine, for instance, what we are doing when we program a machine is to use the grammar of some computer language to convince the computer to do something for us. Well, that's exactly rhetoric. That's what man, human to human rhetoric does. I, I try, for instance, at this moment, I'm trying to articulate ideas with you and convince you that I'm right, or I'm addressing the field properly. So in a sense, we now need to master these two forms of communication. And they are related, as I will try to explain. So it's perhaps a little bit too much to say that programming is human-machine rhetoric, but it actually fits the frame. It fits the idea. So that's why we call this new setting the new trivium. Why? Because one needs the mother language, because it is, after all, what we use to communicate. And if I want to tell one of my students, write this program, I don't give the program itself. I just tell, write me this program, and I'm going to describe this program in some language, some natural language. So one needs to understand natural language to think of, in the next step, program what is being asked, and that's computing. And as I will try to explain, mathematics is here essential because that's actually the way computers capture information. Let us leave that for the second part in more detail. So this we call the new trivium. It's still three disciplines, but now computing is taking the place of the rhetoric. So NSICO is an association, as has already been mentioned by Luis, and the aim is to be able to make computing a new course subject in pre-university education, 12 years. So instead of teaching technology, we want a scientific syllabus, along with maths, physics, biology, whatever the students study. So that's our aim. Whether we are going to achieve it, we don't know, but we're working strongly towards that direction. This project started in 2020, and the first experiments were done in 3 schools in Portugal, and that's the beginning of our pilot project. Currently, this pilot project has 100 classes, 2,200 students, and typically it runs 1 hour per week in these schools. Who are doing this? Of course, the direction. Of course, us, this team of 3 people who are producing the contents for the classes and actually preparing webinars like this one, and also a group of very young and highly motivated tutors, which are called master teachers, who are actually giving the classes, okay, in each school. And of course, with young people, you always think of innovation first approach. We have some golden principles in this teaching. The first one is that the computer is not the aim, it is the means. So we want to avoid what we called old-styled ICT academicism, okay? It's onwards teaching in the sense that we always start from something the students already know, probably outside of the computing realm, but that's what we have to expect. And interestingly, history and storytelling matters. in this education as we have experienced in the classes. Let me give you an example. At earlier or later, students have to get acquainted to the binary system of representing information, the zeros and the ones that computers understand. And we were thinking about introducing this and how. And eventually we realized that it had to do with games or whatever. And we found that the Space Invaders game, created in 1978 by this Japanese computer scientist Tomohiro Nishikado, and we realized that his book, the booklet or the notebook that he used to start thinking, plan or to implement or to think about this game, became available on the web. And we see from here the method that he used. So basically, it started from realistic images, realistic drawings, and did an approximation of these drawings in terms of a reticulated system with the white cells and black cells. And we took this as a good starting point. Why? In a sense, it's historical, so it has this historical flavor. And on the other hand, it's like telling the students, the young people, if he did it in his computer, which at this stage was just a notebook, we're going to do the same in our notebook. And this is the Ensico notebook that you see here on the right, this blue covered booklet. And that's what we call, this is Portuguese, but this is my first computer. So this is the booklet that they receive in the first day of the classes. Sometimes they feel a little bit disappointed that they are not given a true computer, but eventually they realize that doing computing has a lot of work which is not physically attached to computing. We need to think what we are going to do, and they deal with this. And they like this very first computer, and this the fact that we start from a computer, which is a booklet, already has in it, carved in it, the unplugged method. They are going to start studying computing using a notebook. So if we did it, we are going to do it as well. And so this is how we start. First, this is just drawings. They draw all these black squares, and then they are introduced to colors and that other kinds of things. But at this stage, then they are confronted with this idea. How does the computer, how can you actually port or move or make the computer understand this is just a drawing? And that's where the convention of replacing white cells by 0 and black cells by 1, whatever these 1 and 0 are, that takes place. And then we start replacing the black squares by 1s and the white squares by 0. And we have just landed into the binary representation of information, bitmaps. And in a natural way, as I said, coming from something they already know or something which comes from the outside. And what happens is that once you reach this stage, there's a lot of computer science that you can already teach. Why? Because from the little images of the Space Invaders game, then you start to invent your own little images. Then you start thinking of approximating letters. So in a sense, this is digital scanning of symbols. And sooner or later, they are studying other things like, for instance, QR codes. Why? Because at some stage, we start playing this game, which is, well, the image, these images, we could survive. We can represent them inside the computer. But what about letters? numbers, how are they represented? But they already know about this positional system of of size 2, so only two numbers, and it opens a wealth of interesting paths, teaching bits and bytes, numbers and letters, Morse code, which is a quite successful piece of teaching. They like this very much. Braille, understanding Braille, QR codes, and so on. So to teach them how to represent letters in this system, we use these binary trees. Of course, we don't tell them these are binary trees. It's just a way of following these paths, which you open, because if you have more letters than what you have, what the branches of the tree are, you just add another level, and this is quite simple for them to understand. It is our experience that starting it this way, all this come out naturally. So the 4 cells here are going to be represented by filled with zeros and ones, representing a particular letter. Then they study encryption and decryption. And it's interesting because with so little, you can actually teach quite a lot, in a sense. Of course, in a superficial way, but already the concepts, that's what we privilege. The concepts are slowly getting in. So, as I said, this is a concept-first approach. Understanding the concept is way more important than mastering the technology. And this is important because, I mean, in more than 40 years in my teaching, I've seen concepts remaining and technologies fading away. When I started programming, I used programming languages which have just disappeared. But the golden principles of programming, which are not inside the programming language, they are just theory and conceptual notions, they survive, and they are the same. They are completely the same. So we don't want to be attached to a particular technology, although at some stage we go plugged. Okay, but I'm just telling you how we start. We start from the unplugging setting. The other thing is that teaching children from such young age, we have to modulate the kind of knowledge they're going to acquire. This curve thing, which in a sense is a transition from a 0 to a 1. The 0 is just subliminal knowledge. They are learning without being aware of it. I will give you 1 or 2 examples. Of course, I'm not going to cover many examples. We have done many experiments. This pilot project is intended to be experimental. We're experimenting, but in a sense, for very, very young students, they need to be told tales. They need figures, like we have figures, characters, to fairy tale like thing, and somehow in those tales, hidden in them, there is this subliminal knowledge that they are going to is going to germinate, is going to start, is there, and then it's going to grow in later stages. This stage, what we call implicit knowledge, they are given games. I will give an example of one. They are given games, and what they are learning is more explicit, but not yet totally explicit. It's what we call implicit. I will give you an example of this. And then, through the guidance of master teachers, we reach the explicit form of knowledge, which in the beginning is unplugged, as always, because as a software engineer, I always think about my programs. My first step when I need to write a program is not start keying in a computer. I just start thinking about it, and that's the way to go. And this is this guided process. In this case, we already use an environment where they can actually start by using programs that have already been they are available. That's the first stage. Use before create. They start using, they start combining them, they start composing them, in a sense, dividing difficult things into compositions of smaller things, and in a late stage, they actually start programming. So these different steps of this process, it's what we call teaching style modulation, starting completely unplugged. Then we reach a stage which we call pseudo plugged, and I will give an example of this, and then we go plugged. Okay, and one of the very important things in our view of this strategy, of this architecture, is what we call backwards teaching. But maybe there is a better term for this, because this is just, we are not trained into education, so maybe we are using the wrong words, and maybe we are but what we call backwards teaching is the following. We always work in this way. Suppose in this third phase we want the students to know that we want them to do something. That something needs to be prepared, and it needs to be prepared the implicit phase, and then in the subliminal phase. So we have to always go backwards. So it's a backwards thing. We just say at year 9 they should be able to do this. Well, if we want them to do this at year 9, what should they do at year 7? What should they have done in year 5? And so on. So, and we are quite careful about making sure that all this makes sense. Still, golden principles. Computing should not spoil the child's brain. We know that digital technologies are not doing very well in this respect. We know that there's a lot of discussion about the impact of mobile phones and that kind of thing in the ability, the child's brains. The other thing is that we have to separate studying computing from entertainment, although it can be interesting and entertaining to use a computer, but it should be hard work. Well, it's not hard work by definition. It is as hard as the other disciplines. Maths is hard work. Mother language is hard work. Teaching a foreign language is hard work. So this should be at exactly the same level, and not a second level course, which you do when you have time, okay? And computing is far more than using computers. And as our unplugged method shows, you can actually do computing without a computer. There are also some misconceptions. Sometimes I think that technology marvels the educator more than the student. It's our experience that sometimes they don't feel excited about something in the plugged phase that we are going next week. They are going to do computer graphics, for instance. This was one of the cases, and they were not so excited about those computer graphics. Well, there was something interesting. They were doing the graphics without using a computer graphics thing made by somebody else, but they were not very excited, telling us the following: whatever we do is always behind. I mean, in terms of technological marveling, it's always behind the computer games and the apps that they already use in their mobile phones. So sometimes we see the educator more excited and the students not so exciting. The other misconceptions, and this has to do, I must say, I don't know if this is more general or more widespread than this, but here in Portugal, when people talk about computational thinking, they sometimes say that debugging, I mean, people should understand the way programmers debug their code, and starting thinking in that way when they are dealing with other courses. I mean, I must say that as a programmer, I'm ashamed of debugging. Ashamed in the sense that debugging is the proof that you cannot solve the problem. It means absence of strategy without being a strategy. So I hope this misconception is clear to other people, because you debug something. For instance, you cannot debug a bridge. You cannot debug a building. If you start debugging a bridge, perhaps it's going to collapse. Okay, so this this contradicts all the golden principles of engineering, and this is important to stress. There are many plugged approaches. Our isn't plugged in the first place, is unplugged. But for the plugged approaches, it's a code-first approach. Our experience is starting to teach code is not right. It's far more difficult because, as I will explain in the second part, data always precede the algorithms that manipulate them. If you want to do cooking, and cooking is done with recipes, and the recipe is the program. The very first thing you need is the things that you are going to use in your recipe. So things precede recipes. So and data is far more intuitive for kids to understand because data is there. Is something they can perceive. And also algorithmic culture can be taught in quite different ways, as I will try to explain in one or two examples. So to summarize this first part, I hope I didn't go out of time. Our project at NSICU, we understand, is an out-of-the-box education project. It goes very much against much that is being done in computing education in schools in many places, but this is the approach that we believe is productive. We are learning by doing and not just following others. In a sense, we decided not to follow not because the others are wrong. No, it's just because we want to test things that are not by the book. We want to fight the digital drug syndrome, which is a real problem. And the more sometimes I think in these terms, very young kids nowadays have mobile phones. So schools tend to boast their idea, their facilities, saying that we have computers in school. Every student has a computer. Well, they don't need a computer. They already have one in their pocket. Okay, it's a mobile phone. So it's not technology that they need. They need concepts. They need to be able to mount a strategy when they are faced with a difficult problem. Final lemma, learning and teaching is great fun. I can tell you this, well, I've been a teacher for a long time. If I didn't think this, I would have dropped out of the university and do something else. So this is the first part. So according to the organization, now I keep my slides, but now there is a little interval for question and answers. Luis, can you?
Yes, yes, that's true. So we'll now just stop a little bit, show just a few minutes in order for you to put questions. Okay, there are some of them or some comments already in the chat, but okay, we have I think we have some hands raised. Okay. So let me just check if I think I saw one hand, right?
No, I don't think so. It was just a reaction.
Okay, okay.
But don't be shy.
Yeah, don't be shy. So feel free to put questions that you think would be relevant for our discussion today.
Or we can
and
have
by the way, sorry.
We can have all of them at the end because.
Yeah, of course. Tinez, you were saying?
I was saying that there are some comments in the chat about Huffman compression codes. And we actually do teach kids Huffman compression using binary trees. So that was interesting.
Yeah, it's one of the
We
talks,
also have another question which says, what is the curriculum you created? Well, we are creating it right now at this very moment as we go. So we didn't lock ourselves in an office and just thought theoretically about what we wanted to teach. We are actually creating the curriculum and testing it in real time. So we haven't done all that work yet. We are working on it, but we are thinking from ourselves and following our principles and what we think is correct, not only what the others are doing and following trends.
Yeah, with respect to schools, yes. So we are in fact at this moment working with 20 schools in Portugal, okay, and covering 2,000 students. But our main goal is to create all the conditions together with the local entities and the governmental agencies in Portugal in order to have this computing discipline in the mandatory school. So in Portugal, we have 12 years of mandatory school. And so, as Inez was saying, we are creating this curriculum for these 12 years. But at this moment, and until now, we have been focused on the first 9 years. Okay, so we are what we call here the basic period of these 12 years. And so we are covering the 3 cycles of this basic period. Okay, so the 3 cycles means that the first cycle we are talking about kids between 6 and 10 years old. Then we have kids between 10 and 12, and then we have from 12 to 15. Okay, so that's precisely what we are doing at this moment. Well, with respect to the curriculum being available, so until now, this is not publicly available. Okay, so we are working together with these schools and with the people that are working with us at INSICO. But we expect not only here, okay, in this consortium and in this particular Erasmus project, we are starting sharing our ideas and sharing some of the contents with our partners and also with European and other countries. Okay, like we have here people from different countries rather than Europe, but in order to be publicly available, we are thinking about 2025. Okay, so until then, we are mainly working on this curriculum in order to put it available, officially available for our schools. And at the same time, we are also discussing how can we put this available in other countries. Okay. About how do students feel about notebook approach? Well, it's really very interesting, that question, and the things that we are learning from our students when they are using their first computer, so our notebook. And the good thing that I can share with you, and for engineers can also share lots of things with respect to this particular topic, is that they really enjoy the notebook and they really um, want most of the times to do activities in the notebook, so in paper and using pen, rather than go into and directly to the computer. Okay, just because since we are talking about intellectual activity, they really enjoy learning how to learn these things and also how to apply the knowledge in things that they know that they can be used and they can be explored using a computer later.
Luis, can I just say something?
Yeah, of course, of course.
I would ask Inês to tell that little story about the battery. Can you do that?
Oh, of course, yeah. um so our students have a lot of creativity, especially the younger ones. So Most of them never call the notebook. They call it computer. So if you call it notebook, they get angry at you because it's not a notebook, it's a computer. And one of the students says, oh, this is even better than a computer because it has infinite battery. It never runs out of battery. And that's fascinating. So they really enjoy the notebook, and like it's the design is very pretty and they feel like a special connection because it's not just something they can buy in some store. It is sort of personalized. It's for them, made by us for them. So it's just they feel part of this computing community, and that object represents much more than just a simple notebook. That object is knowledge, and they do see it as a sort of computer where they solve challenges and all of that. Now we have a raised hand.
Yes, and and
Perhaps.
Paul, you may use your microphone and your camera if you want to.
Hello.
Hello.
Thank you very much. I'm very much enjoying this session, and it's a pleasure to meet you all.
It's you too.
I'm just looking at this NetCAD system, looking for these materials that you're showing us now, and it keeps on skipping between saying, the English only version available at the Python enrollment link. But when I go into this course, it says whenever I click on a session like the introduction or even this first part, the trivium, it said that this course is not ready to be taken. And I'm wondering if there's something that's missing or something you could help with.
Yeah, so Paul, this is a series of 4 webinars, okay? So we'll have 4 webinars. This is the first one, okay? So on these 4 webinars, what we'll explain to you is this first one will give you a general overview of the methodology and how are we doing this when we are talking about teaching computing in the mandatory school, so the first 12 years of school. Then in the second and third webinar, we'll go deeply into what we teach young kids and what we teach in kids that are in the middle of this 12-year learning process. Okay. On the last one, we will do a webinar that will be completely focused on Python, on the Python language. Okay. So in a sense, and in other words, Paul, in the first 3, we will talk about computing in general, and we will in fact also show you, for instance, today, some things written in a language that is not Python, is Haskell, for instance, in which you will understand concepts like sequences and how you would deal with sequences and so on. And then in the second and third webinar, we'll also use mainly Haskell, but again, to introduce and to explore the concepts that are related to any programming language. And on the last one, that will be led by Open University, you'll have a Python-oriented training mini course, okay? But of course, try exploring more deeply some of the ingredients of the Python language.
Thank you very much. Much appreciated.
No, you're welcome.
Thank you. I think we have time for this last question here in the chat. So have you found any difference in the genders and how they relate to computing? That's a very interesting question. And the answer is basically no. Both girls and boys and everything in between show interest about computation, and everybody wants to learn. They really like the things that we teach. So we see no difference, not in understanding, performance, curiosity. Like there is no difference at the level of understanding and learning about computing. However, some of our master teachers reported that when it becomes a little more technical and just like actually using the computer and all of that. Sometimes in some classes, there are groups of girls who do not show that so much interest. But at the intellectual concept level, the interest is the same, and the performance is, it is good in both genders. Uh, Maybe there's a little difference when it actually comes to put the hands on the computer. Maybe the boys are slightly more motivated to do that, but there is no big difference really.
Okay, shall we move on?
Yeah, if there is no further questions, again, we will stop again at the end of part 2 to allow you to put further questions. But for now, I think that we should proceed. Yeah.
Okay, thank you. Thank you for the questions. Now, in this second part, I will try and be a little bit more specific. It doesn't mean that the curriculum goes exactly in this way. This is actually addressing middle stage in this education program. And that's when we are confronted with this problem of what should we teach first. And I'll try and be address this question, which is basically where does one start when one goes in this direction. And I think what's obvious is that we should start from what children already know, because if there is no link to things they already know, it's going to be something strange and doesn't connect and doesn't stay together. So we know that there are things around us. That's what a baby starts when it starts looking at things. It's just aware of things one after the other. Okay, but eventually we are able to do actions, to do things. Things are the nouns and actions are the verbs. So again, you see the connection with the mother language, which is important. And actions transform things. If I blow a balloon, it is transformed from a wrinkled balloon into a round balloon. When you start painting a drawing, it gets transformed. When children play and run, they are transforming their physical GPS coordinates, okay? If I drop pebbles in a bag, it transforms the bag, it gets heavier. So there is this idea that our actions transform things, which is very much related to the physics of information and things like that. And this is important because, as we will see later, the students quite understand this quite well, the transformation process. Also, things can be observed and measured. The way we tell things apart, and children, of course, do it in this way too, of course. They're very, 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 and they're actually far more intelligent than we thought, because they are parts of this syllabus that we were thinking later, and then we're experimenting with much younger ones, and they are following it. And of course, they tell things apart by observation. So when we gather our observations, we have information. And the collection of our observations about, for instance, one object is a mental model of the object. Is not actually the object. It would be physically impossible according to the laws of physics. Okay, it's actually our view of reality, our mental model. And mental models are more abstract than the things they model, because they are details of reality which doesn't interest us in a particular situation or context. Okay, we can once we have these mental models and we have some command of some language, we can start talking and writing about our mental models of things. We use words for that. Putting words together, we make sentences and we write texts. Now, communication, which is basically what we want to do when we use a computer. We are trying to communicate with the machine. It needs a convention. And as in human communication, one needs languages. These are the programming languages, but they are languages. They have a grammar, okay? And the program is incorrect if it doesn't follow the grammar. Actually, the languages are classified. The computer science intersects with linguistics when we start classifying languages. Some are context-free, and who classified these languages? They were not mathematicians; they were linguists. So we're following a grammar, and of course, language is important because without it, we cannot communicate, be it with the machine or with a human. Now, we start thinking when we start using our mental models instead of using the things themselves. When a dog wants to cross a river, it's of course I don't mean the dog doesn't have any a mental model, maybe they have, but it's trying to cross the river by experimentation with a physical thing. We learned to do it differently. We start thinking about things without being in presence of them. We have our mental models of those things, and this has been done. It's in several layers of sophistication for ages, in physics, in engineering, in philosophy, whatever. What's important is that we always filter irrelevant details. And when we think about programming, this is one of the key issues. We see sometimes programs more complex than others because they have junk, what we say junk. The mental model is larger than necessary, okay? But we are trained to do smart observations and to filter those details. So this is thinking. What is abstract thinking? And don't forget that the title of this second part is computational thinking. Abstract thinking means that we not only have mental models, but we are able to express these mental models mathematically. And with these mathematical objects, we can actually calculate solutions without experimenting them. And now there is something new here, mathematics. What is that? It's just another language. Yes, it is. It is another language, but it has two main ingredients. It is formal, so the grammar is less flexible than the natural language, but it enables deductive and calculational thinking. And it is when you start mathematically modeling your problems or your solutions mathematically that science begins. And this is a major step in human history. Now, computational thinking, what does it mean? How does it compare to abstract thinking? What's new? I would say there's not much new, because what we are going to do is to seek help from a machine to encode and solve the maths of our models. The machine is powerful. Actually, the machine is quite stupid, very stupid in the beginning, doesn't know anything. But if we are able to teach the machine through our rhetoric, okay, correct, to understand the models, then it can go very fast, in very far, as we know. It all started a long time ago with slide rules. I mean, I remember I still used a very long time ago, used these slide rules in my early education. So this is when things start seeking. So what we're doing, we have our mathematical models, and we are using machines, or starting to use machines to help us. This is interesting because when we think about the early stages or the archaeology of programming languages, we reach 1950s. In the 1950s, one of the first languages, Fortran. Fortran is formula translation. So we see exactly this program. We have already a mathematical model of the problem that we want to solve. And at IBM, they designed a language where you could encode the formulas of your model and then translate those formulas into machine codes. So in a sense, it's the cradle of software as we know it. And we have here the picture of John Bacchus, who was a very prominent computer scientist and was the designer of Fortran and much more. But let us just mention his role. And so, in a sense, this Fortran language already tells us that what we need computers for. We want them to understand our formulas and to behave accordingly very fast as they normally do. So we all know this. There was an amazing evolution. Digital hardware is regarded as one of the main inventions of all time, in particular in the current highly sophisticated technological setting. Enormous amounts of data are processed very fast, and software is everywhere. It's unavoidable. Yet there is a problem. And what is the problem? And the problem is far from being solved or softened. The problem is the new trivium, is mastering this new trivium. Because now you need to know three things very well. You need to be able to express yourself in your mother language, or a foreign language is the same. And we want to communicate our mental models to computers, but computers only understand mathematics. So we have now to play this triple game of being able to express ourselves in these ways, where the computing part is the mechanical part, of course. Computational thinking, what is this? Well, it does not mean that we should think like a computer. I must say, as a human, that we are far better thinkers than computers. What it means, it rather means shaping our thoughts, so our mental models, into a format that a computer can understand. And computers, it's a fact, can only understand formal mathematical models. Even if our languages, the languages we use, don't show that mathematicity, that maths part of the things that the computer handles, it can only handle formal models of things. For instance, these days there is this ChatGPT language model. Is a huge language model. If you go into the machinery that where this language model that implements these language models is quite heavy maths. So even something which nowadays people are experimenting and which people interact with using natural language, that natural language is converting to vectors of a huge linear algebraic system which is processed. So you can see that there is no way of running away from this. So what is the challenge? The challenge in particular in the program, and I think everybody is thinking in these terms, and SQL's program wants to start teaching computing from year one, okay, is to teach children of young age how to build mathematical models without explicit use of maths. So this is the first challenge that we have. And off the record, we have a setting which is not good for this, because there is this math phobia thing. And this math phobia thing exists perhaps because we have not done this program of starting very early. We are starting too late. And so perhaps this is one of the reasons why this math phobia thing exists. I must admit that even at universities, teaching computing, or at least programming, is pre-scientific, is not truly scientific. And teaching computer programming is perhaps the most unsuccessful in the whole STEM field. When we look at the effort that is put on making instructing programmers how to program and how badly they program, it's kind of a failure. So there is a need to start much early, very, very early, so that you give time to the brain of the little child and then boy or girl to eventually reach the high standards that are needed. So the broad picture you already know is just being a little bit more specific here. Unplugged corresponds to subliminal, pen and pencil, drawings, tales, games. the pseudo plugged, what does this mean? And we've realized that this is quite effective. So the students still have their notebook, their computer, but the teacher is already using a computer. And so the teacher is plugged, but the student is unplugged. And what they are doing in their notebook is then confirmed by the experiment by the teacher. And the thing that normally works very well is, for instance, sorting. If they are going to sort 5 numbers or 10 numbers in their notebook, sometimes the first question they do, I don't need a computer for this. I can order the numbers myself. Okay, it's very easy. Well, it's only when you ask them, I ask you to order me these 1,000 numbers, that they say, I cannot do that. They are too many numbers. And that's when we tell them, well, you see, now the size of the problem is much higher, much larger, and we need computers for that. We only need computers when the size of things is intractable by our brain. Well, we could actually do that. We know that but the human brain is very special. It doesn't accommodate very easily with routine, and when things start to be a routine, we just start making mistakes. The plugged is not very much new here. Is basically the student is as plugged as the teacher, and they start writing and running code. Unplugged mode. Let me just look at the time. Subliminal teaching. Let us think, for instance, of this game. I don't know if you are seeing my only the slides, right? Not my Teams little window. Okay. So here is a game that students can play. That we may ask students or kids to play. They can actually be, this can be done in the notebook, or can be played with pebbles in chessboard like chessboard, or even played in a floor where the floor is divided into these 64 cells, which sometimes you might have. They can, if they play it on the floor, then you may imagine them having T-shirts with these numbers, or having, the numbers in there. And now let us play the game. So this is a game. Okay. So let us do it. Okay. So it's a game like any other. It has rules. It has a starting position. It has a final position. The pebbles go from yellow to blue. Some rules can be changed. Basically, what happens is that one of the pebbles goes blue, goes to the second row in the middle, and this red line is traced mentally, and now the numbers, the pebbles smaller than this pebble go to the left, and the others go to the right. And then the process starts all over again until all pebbles become blue. So what is this? This is subliminal teaching of sorting. Basically, it's subliminal in what sense? Children are playing this. They understand the rules that we tell them, but they are unaware that, in particular, if they are dancing on the floor or playing on the floor, that they are the data. They are the numbers that are manipulated by an algorithm, which in this case is quicksort, encoded by the rules of the game. Okay, this is just a game. We don't dare speaking this word quicksort. Okay, we just ask them to be aware of the final outcome of the game, where the numbers are sorted. For instance, they are unaware that when all of them become blue, so all of them have played the pivot role. They form, as you see here on the chessboard, they form a binary search tree, which is by ordered. So it's what's called a binary search tree. And they will much later understand that the essence of this quicksort algorithm is this tree. Okay, so, but that will take years to reach that stage. But we believe that the fact that they have danced this and is going to stay there for a long time, eventually it starts popping up, and at some stage we might say, you remember when you danced that game, and so on and so on and so on. That's quicksort. Let us now make it explicit. So this is just an example of subliminal teaching. Pseudo-plug teaching, well, again, we go to the things that we can see around us, the actions that we can do with those things, which are transformations of those things. Well, and there's a book which is very well known in the computer science domain, written by a Swiss computer scientists, that just tells an equation which is easy to grasp. If you want to build programs, you need algorithms and data structures. Later, he realized that the title is in the wrong order. It should be data structures plus algorithms equal programs. Well, of course, addition is commutative and it's not a serious fault, but what he conveyed when he said that the title was wrong is that data come first. They precede algorithms. So our overall plan is now at this stage in this to start talking about things to be modeled by data structures, and to study and to start talking about actions that will become more or less sophisticated, the algorithms that will learn at some stage later. Not now, not much later, because we are moving on in this subliminal, implicit, explicit path. And now, which data? One thing that we have observed is that positional information is very easy to grasp. So the subliminal notion of sequence is easy to see that the kids understand very well, being first here, being second there. So it's very easy for them to identify if you are ahead or if you are behind. It's very easy for them to count people that are, for instance, in the queue. So maybe this is a good way to start from, and indeed it is. Because this is so intuitive that a vocabulary can start being introduced, which later is going to be names of functions or of operations or methods on sequences. The head of the sequence, the tail of the sequence, and then in reverse order, the last in the sequence, and the initial part of the sequence, which is the sequence, but the last element. They can also very quickly sense this idea that the sequence can be reversed. Those at the end become at the beginning. And we are aware, we have experimenting with this, and it's a success to start from here. So we can talk about, for instance, first, just writing the words of the things that are going to be in the sequence, and start putting commas around those things. Then there is a need for something telling beginning of sequence, end of sequence, so open bracket, close bracket. And now with this open bracket, close bracket convention and comma separation, we can start having sequences, finite sequences, without any limitation. For instance, stacks. And it's very interesting because in many cases, all this is metaphorical. There is nothing more metaphorical than the computer science language. We are always, when we choose a word to describe an abstract data structure, we normally pick words from outside. They are metaphors of the outside. Stacks are clearly a metaphor. And the mental model is that you have things on top of each other. The abstract model is that the stack is a sequence, whose element at the top is the head of the sequence. It's very easy for a student to see. Compared to the previous sequence, the only thing which happens is that is now 20 degrees rotated, and now it's vertical instead of being horizontal. Counting the number of books, very easy. So now stacks and queues are sequences, and it's time to bring the abstract model explicit. And here we are already showing a piece of code. We don't tell them that this is code, but this is already code. We are telling that this stack of books, it has a green book on top, then a blue, red, yellow, and purple. So when you have these, you can actually start querying the model. How many books are in this stack? This is, recall the trivium. We are in the mother language here, or in the language. Let us ask the same in other words. What is the size of the stack? Well, what is the size of the stack? We perhaps don't need the definite articles and the verb shorter. The size of the stack. This is what matters in this query. Even shorter. Size stack. This is code. So you remove the size stack. This is code. If you have this stack, and if you write size of stack, so you are observing the stack, you have number 5, which is the number of elements of stack. So now we have we are fulfilling the path to the computational thinking. This is actually computational thinking. How is it born? It is born out of mental models that we express in our natural language, and maybe graphical, okay? And it goes abstract and then goes computational. And there is no way, I don't think that, some people think that you are thinking computationally when you are using a computer. It's not true. I can have computational thinking without a computer, and somebody else in a computer is not thinking computationally. So in the picture aside, you already see the same thing, but now in a Jupyter notebook. And it's just it is a very first picture of something you are going to see in the part 3. Okay, you see that in this Jupyter notebook, you have the declaration of the stack, the definition of this stack, as you saw in previous slides. And in text, you have what is to be queried, and in this cell 4, you write, this is already code, size stack, and it gives you 5. Well, now let me just say something about the actions. How do we, so you clearly see, I've not shown you code, for loops or while loops or that kind of thing. This is the last part of our process, because actions come after data. Once you have data, you can start thinking about the actions that transform that data. And it's quite easy, because as we have modeled things in terms, in this case, sequences, there is a whole vocabulary that we can use to start transforming those sequences. For instance, picking up that queue that we started from, we can, by analogy here, who is the head of the sequence? Well, it's the first person, so this is this person here, and the remainder, the rest of the list, is the rest of the queue. Okay, perceiving reversal is very easy. Reverse is a transformation of the queue, where the last element of the queue goes first, and so on. So you see the magic thing here, which is the object, in this case it is a queue, before the application of the transformation, reverse, that reverse is the queue. And that's basically how we start teaching the manipulation of data, so through functions that are already defined. It's far better to teach students how to use functions that are already available as a vocabulary, combine them in more and more sophisticated things, expressions, doing more and more and more, than asking them to write a for loop to do this or that. That's a last stage. So the actions transform the queue, and here you have another image of the Jupyter Notebook that we use in all our classes, in the plugged part of our classes. And so you see here, and you ask the students to write this at some stage. Here is the queue, and then you apply the transformation reverse, and you have the queue reversed. And that's now what they do. What do they do next? Now the thing that comes off after this little triangle goes more and more sophisticated. Functions composed with others, because this is and so you see that they can actually be doing this sorting or this reversal in their notebook. And at some stage, the teacher said, "Let us confirm that that what you have done is correct." Okay, and later, for a queue much longer than this. In this language that we are using, we actually have infinite lists, infinite sequences, which is, in a particular context like series and all that, is very easy, is very handy, because we actually have in the language infinite sequences. So in this pseudo-plugged code mode, the computational model, the computed model, is handled by the teacher as a kind of confirmation and scaling up in terms of dimension and quantity of what they've done in their computer, which is the notebook. So we see that this new trivium thing blends mother language with computing in a way that leads naturally to a functional first approach. Here I have to be succinct, but I could be more specific and tell you how what we write on paper or what we speak can actually be translated, manipulated until you reach the kind of SMS, short message that you send to the computer. So there is this game, you have an object, you have a transformation, you have a new object that you pass on to another transformation and so on. Of course, chaining these transformations is nothing but functional composition. And it's interesting because it arises very early in our way of teaching computing, so much so that when function composition, which is then studied in year 7, I think, or 8, when the students reach those classes in maths.
In Portugal, it's only in 10th grade, so when they are 15 or 16 or something.
10th grade, so you see
Secondary education.
Our little girls and boys are studying this so early. Okay, again, so I'm sure when they reach those year 10 or year 9 or whatever, they have done functional composition lots of times before. Okay, so and they have learned something which is very, very important, is how to divide difficult actions into simpler actions by putting them together, combining them together. And the first combinator they study is this triangle, is this transformation of an object to by a transformation. And this is very important because because there is a link to the parallel education in maths, even though in Portugal function composition is taught very, very late, I think. But anyway, and it's something that I would say the politicians will be fond of, because it's preparing the students for maths. So in a very intuitive way, they are not in the Cartesian play with coordinates and that kind of thing. They are just transforming things, and this is already functions and applying functions to objects. And it actually motivates, I believe, students to learn maths and fulfilling the purpose of this new trivium. Well, there is not much new in the plugged mode, apart from the student now having access to these notebooks. So after they understand the concept, they can go to the notebook and just follow the Jupyter notebook is also a notebook like the one they have, the physical one they have, but this one is virtual, is a computer notebook. And now they start what they're doing in their notebook. Now they start playing the piano, as we say. Okay, and they handle the computational models. Now, one may ask, what comes next? Okay, sequences. You may say, okay, I'm convinced that sequences is a good start. Well, the next thing in our experience is pairing. Pairing is very important. And the notion of a pair is very intuitive. When they join hands, they form a pair. So and these transformations, like swapping the order of the pair, is another very intuitive concept. And what's interesting is with sequences, finite or infinite, but let us keep them finite. With finite sequences and pairing, you can teach a lot of computer science concepts. You can teach the Cartesian coordinates, of course, and then you can start doing computer graphics, and you can start telling them about graphs, uh, social networks as graphs of people and that kind of thing. We can teach them automata, very soft automata theory, but they are introduced into automata and so on. So with very little, we do much. And that's, we believe, one of the merits of this approach, which is let us start from very small things, but powerful enough to fuel more and more elaborated concepts. Eventually, year 9 in our experiments thus far, maybe earlier, we don't know, because we are having this surprise. I must admit, I am surprised that younger kids, younger than I previously thought, master these concepts, because we're not talking about technology, it's concepts in this plugged mode supported by the technology we're using. But for instance, the other ingredient, and I think in the demos that we are going to do today in the third part, we're going to show that this very first principle of composition evolves towards another generic compositional strategy, which is divide and conquer. And we divide and conquer, which is taught very carefully, okay, but and again, kind of subliminal in the first place, they can address whatever problem can be solved by a computer, because all algorithms are divide and conquer algorithms, even if they don't look like. Okay, so we basically solve a complex problem, the processing of a difficult data structure by splitting it into parts and recursively, either explicitly or not, solving the subparts and so on. So this is as far as we have reached in our experiments, teaching them how to start writing programs that run in this way. So let me summarize. Our overall principle is what is captured by this idea of this: keep it stupidly simple, and I must say, cheap. It's very cheap teaching, because we don't depend on technology. It can come early if, I mean, the school has means for that, but a school who doesn't have any means for buying computers or whatever, we can go from year 1 to year 12, just, conceptually. Our choice of technology is everything is web-based. So no installation of packages, nothing is a nightmare. I have experience about that. Machines with operating systems with different operating systems, and every machine is different from each other, and it's just in a kills time. So everything is web-based. Our metaphor here is the booklet, the physical little notebook, is transfigured into an electronic notebook, and this electronic notebook is the Jupyter notebook. And as I tried to explain, our connection, the connection that we make between mother language and computer language, leads us naturally to the functional first paradigm. We don't mean that we're going to be functional all the time, but this is the get in door. Okay, then we can go on and later introduce them to whatever language or whatever paradigm that exists out there. But the beginning has to be very careful. And thank you very much. This is the end of part 2.
Yeah, and so now again we'll just have 2 or 3 minutes to let you put some questions if you want to. And then we'll just do a first a short break before entering into part 3.
I think I can stop sharing. Okay. Is that okay, Luis?
No. You can. We can see these slides for just 1 or 2 minutes.
So no questions? You can either raise your hand or write in the chat.
Yep. Well, thank you.
Yeah, thank you for all your supportive comments.
Yeah, absolutely. Okay. Well, just to introduce the third part, okay. And on the third part, you will also participate through polls, okay, that we will launch in specific parts of the presentation. Okay, and at the end of part 3, we'll just show you how to write a very simple problem that will solve a very simple problem with an algorithm, but that will show you how simple things can be done when we have the concepts in the right place.
There's a question. I think Professor José Nuno should answer it. So, why teaching functional at such an early age? And have you had any issues with student understanding?
No, we haven't had any issues.
That's true. I can confirm it.
They are an empty body. I mean, an empty brain. They master whatever you give them. We just believe that the functional view is more natural. It's connected to the mother language. It's also the language that they're going to use or to see in other when they study physics and other things. And I would say that's the complex, again, anti-functional complex comes from the adults, not from the children. The children are very comfortable with this, and they know the rule of the game and they play it nicely. And I believe Inês, who is giving the lectures or has given lectures, confirms this.
Yeah, they understand it very easily. It's super intuitive. Like you have a thing and then you transform it into another thing. So simpler than that, I don't think it's possible. It's really simple. It's a very simple concept, and they just apply functions. They just transform things, and it's supernatural. So there's another question here. Is there any problem with crossover with the maths curriculum?
Yeah, well, here I think it's important just also for you to know that we are teaching computing aside the mathematics, but of course trying always in our classes to talk every time it makes sense about what they are learning in mathematics and what they are learning in Portuguese or in English or whatever. Okay, so and that's really important because what we expect also is to help the students to understand better the mathematics. Okay,
and I think we have examples. We have examples of them in the maths class saying we've seen that already in the computing class.
Yeah, and that happens because we really, and our experience pretends precisely to explore that. We intend to explore and to teach that to our students lots of concepts that they will learn later on mathematics. And one of them is composition, as Inez was saying before, and the professor Zanoni.
Functional
Okay?
composition, yeah.
Yeah, functional
Even
composition.
functions, even the concept of function, we
Yeah.
introduce it really early. And so when they learn it in the 7th grade, so when they are 12, 13 years old, they're like, oh, we've already seen that in computer science course.
Yeah, but again, the magic word here for us is that this should be natural for them. And that's precisely what we are trying to experiment and to check with our students every week, is to feel that they are learning all these things naturally. Because if that works, everything is perfect.
So if there are no more questions, I say we take that 15-minute break and we will start at 6 p.m. the last part.
Yeah. So you can still be connected, and so we'll just take this break, and we'll be back at 6 o'clock. Okay, I will answer, and we will answer your questions in the midtime. So yes, but later on. So I'm talking about object-oriented programming. Okay. Also, for you to understand exactly why we are thinking about all this in the first 9 years. Okay. So we start with unplugged, in unplugged mode, as explained. Then we start using the pseudo plugged mode. Okay. And at the same time, we are already introducing a functional programming language like Haskell, okay, just to do things and to let students start working with these concepts, but already working with a specific programming language. That, by the way, is very similar to math language, as you probably know. And then when we go into what here in Portugal is the third cycle, so we are talking about students with 10, 11 years old. We start then using the language that are multi-paradigm, so in which we can already, if we want to explore some object-oriented concepts, but what we then do between 11 and 15 years old is to start putting them working not only object-oriented programming language like Python, okay, but at the same time, we also introduce them to a programming environment, okay, like using Visual Studio Code or a similar environment like that, okay. And so we'll do all this in order to prepare them for the later stage, which corresponds to the secondary level here in Portugal, which means that we are talking already about students between 15 years old and 17, 18 years old. And at that level, we intend to use a language like Python, for instance, and to explore things like machine learning, okay, big data, okay, data science, artificial intelligence, all those application domains, but of course, assuming that they already have 9 years of computing before that. Okay. So that's the way we are preparing things. Okay, so we'll be back at 6 o'clock. Have a nice break.